Alright, so here's my answer to this your turn. Hope it went well for you. So I wrote a diagram here, a 100-meter building, and the ball's dropping downwards, and I chose downwards to be positive because it makes more sense. For the motion map, I wrote a velocity motion map, and then with the same dots in the same spots I did acceleration. Acceleration again is always 10 downwards. The velocity is increasing. I didn't figure out numbers for that because I didn't know how many seconds it would be, so I wasn't sure how many dots. You could have put, a 0, 10, 20, 30, and so on. For the graph, my velocity time graph, again it goes upwards. What's different about this one is we don't know the time, we know the displacement, and it's that area which is 100 meters. So a reminder that that line goes up, and then when you're talking about what shape it would be, you'd kind of just drop that, wherever the line left, you would just do a vertical line just back to the x-axis, back to that time axis. So that is a triangle, which is 100 meters. I'll get to the challenge in a minute. Mathematically, if you solve this, you can bring out your big 5. The initial velocity is 0. The time we don't know. Time is what we want to figure out because it says how long. Delta y is 100 meters. Since downwards is positive, it's a positive 100 meters. And acceleration, again, since downwards is positive, it's a positive 10 meters per second squared. So I put the numbers in. And you'll see me again, the VI, or the V1 is, VI, pardon me, is 0. So that first term turns into 0. So we get 100 is equal to half times 10 times delta t squared. Now notice something interesting about the math here, so I'll just stop it right there. I've got time squared is equal to 20. So let me just, think about math for a second here. So let's say if I said x squared was equal to 4. And I'll say, what are all the different possible values for x that would give me the answer for that? Well, x could be equal to 2, because 2 squared is 4, but actually x could also be equal to negative 2, because negative 2 times negative 2 is also 4. So similarly, in this question here, and I've just, I want to go the extra mile for you here, when delta t squared is equal to 20, that means that delta t could have been positive square root of 20 or negative square root of 20, which is actually positive 4.5 seconds or negative 4.5 seconds. What does that mean? Can we have negative time? No, in this case we can't really do negative time, although it would be an interesting discussion. We could have that in class about that. What would that mean? Because there's some good stuff there. So I'm not going to take any marks away if you don't show me that negative version, but you're going to see later on there might be situations, especially with velocity, when you're doing a square root, when you have to include the positive or the negative. So when does that happen? It's like when you have the variable squared is equal to a number, and then you square root both sides, you could get a positive or a negative. So sometimes your velocity might actually be negative, and when you're doing something like this. So just it's sort of one of those places where math and physics have a nice little common intersection there. Let's see if we can finish the challenge part, the solving this graph. Okay, so I said that that area is 100 meters, and because the displacement under a VT graph is the area under a VT graph is displacement. So if I say area is equal to 100 meters, and what is that shape? Well, it's a triangle, so I can say, maybe I'll switch this around, say 100 meters then is equal to 1/2 times the base times the height. So 100 meters is, well, what is the base? That base is some number of seconds. So we don't know how many is going to go by. So I'm going to say delta t seconds multiplied by the height. Again, the height we don't know, and I'm guessing that this is where a lot of people are going to get stuck. Well, the piece that we need to use is the fact that this slope is equal to 10. So the velocity is increasing by 10 for every second that goes by. So if we have t seconds that goes by, how much has the velocity changed? We could say, like, here a is equal to the change in the velocity divided by the change in time. If we solve for the change in velocity, we would get the change in velocity is equal to a times delta t, 10 times how many seconds goes by. So if the velocity started from 0, what would the height of this be? If we started from 0 here, then up here at the top, this would be 10 times how many seconds it goes by. Is that kind of crazy to think of? So we could say here, this inside of here is going to be, the height will be 10 times delta t, because the slope is 10. All right, so once you got that done, then it looks very similar to the other side. I'm going to say 100 meters is equal to, I'll just do 100. 100 is equal to 1, if we multiply this out, 1/2 times 10 is 5. So I'm going to say 5 delta t squared. And then you might notice, hey, it's exactly the same as what we had over here. So it's gonna finish the same way. We're going to say the delta t is equal to the square root of 20, which was somewhere around 4.5 seconds. There, little pen problem. Okay, hope that went well with you. If we turn the page, the second and final example would be if we're standing on top of our school. And you know what, I was looking at this and I think I'm going to change the height of our school. And we're going to pretend it's a very tall school. I'm going to make it 45 meters. That number is actually more friendly than 4, as you may find out in a few minutes. So in example number 2, instead of dropping, we're going to throw this ball upwards, and we're going to stand on top of a 45-meter school, and we're going to throw the ball upwards at 40 meters per second, which is actually pretty swift. It's a very fast throw. So, well, first of all, let's just draw our little diagram here. So here is our building, and again, this building is 45 meters tall, and we're going to throw it upwards. So when we throw it upwards, we're at the top of the building, and it's going to go, upwards, and then it's going to come downwards like that. So the first decision that we need to make is which way should we say is positive. You know what, how about just for a change here, let's say that upwards in this case is positive, because things are going to be going up and downwards, so it might be too confusing to think about directions otherwise. Okay, so what would our motion map look like? Okay, so we would have a dot here, and it's going upwards very quickly. I might have a little trouble here, so maybe I should have started here, I'll draw a new building. I'll draw a new building over here. So here's my building, and for my motion map. So it goes upwards. Maybe I'm even going to say, since it's going 40 meters per second, I'll use my grid mark 1, 2, 3, 4, 1, 2, 3, 1, 2, and then up 1, and then it comes down, getting involved here in that. Okay, and then it starts coming down, and then boy, it's going really fast here, and then it hits sort of over there. Okay, we'll try something like that. So here, to begin with, it's going upwards fast at 40. And then it's going up at 20, and then it's going up at 10, 30, 20, 10. Here it's at 0 at the top point. And now, so if this is going up 30, v equals 30. So again, it's changing. I don't know. Yeah, I guess I do know it's going to take 4 seconds because it was going at 40, 30, 20. Now it's going to be going up at 10. At the top, I'll try to make that a 10. At the top, it's going 0. And now it's going downwards at 10. Here it's going downwards at 20. Here's going downwards at 30. Here's going downwards at 40. Now I don't know how long it takes. I don't know if it's going to take a full another. Well, if it's 45 meters, so yeah, it'll probably be, kind of like, so here, there it's going 40, and here it's going minus 50. I'm not sure whether, exactly how this is going to work. Does it hit the ground just before this last second? So, I'm not sure where, how many seconds, how long it's going to take to hit the ground at this point. So I'll just put a little question mark about whether or not that dot gets done or not. So if you see what I mean, here it's going 40 meters per second, and it's going down really quickly. Is it still in the air at 5 seconds? Does it hit the ground before that? We're not quite sure. So we don't have all the information, and so we'll sort of put a question mark about whether or not that dot is above the ground, at the ground, below the ground. We'll see. All right, so how about a velocity time graph here? So our velocity time graph, I'll make the velocity time graph big here. See if I can draw reasonably straight. It's tough though. Okay, so you'll notice I did some negative, right? Because here would be velocity of 0. It starts off at 40 upwards. So 1, 2, 3. Also, we'll say right here is 40, and then a second later, when we say 1, 2, 3, 4, 5, something like that. So 1 second later, it comes down, and 2, it's coming down like this, and so it's going kind of like this, right? And it has to continue we'll see 6, 7, 8, 9. In fact, let's just keep track here. This would have been, I'll do it in red. Let's keep track of what time. This would be t equals 0. This would be 1 second, 2, 3. At 4, right? At 4 is where it hits this top part, so that's at 4. This would be 5 seconds. This would be 6 seconds, 7 seconds, 8 seconds, and we weren't quite sure about 9. So this would be minus 10, minus 20, minus 30, minus 40, minus 50. Okay, so this is what we have here. So a couple things, right? At the very beginning, the velocity is going up at 40, so that's this dot. It would be this dot here, right? At the top, where it stops for an instant, that's right here. And then on the way down. And this dot here is where it is at minus 40, at this minus 40 spot, and then it goes a little bit farther. Cool. All right, so one thing that we could say, again, remember it was the area is equal to the displacement. And so in this case, it would be delta y. So one thing to notice is that this would be positive displacement. Okay, this is while it's going up. This area here is negative displacement. So it's going downwards. So at 8 seconds, it's gone up and down. It's kind of returned to its original spot. Now it's on its way down. So in fact, if I just put a little dot here, and I'll do some shading. I'll try to erase it afterwards. This space here, this yellow, would be negative area. It's kind of weird to think of. And this space here would be positive area. But those two, you can see visually that they're the same size. Those would cancel each other out. And so this extra area here, this extra space right there, that's how far down it would fall. And here I've got it at 9 seconds, so I don't know exactly what the time was, right? So this space here would be my, how tall is the building? 45 meters. This area is equal to negative 45 meters. Negative because we're going downwards. So that's how high the building was. So if we were to solve it graphically, it's a little bit of a challenging one again, but we could solve it graphically and say that area is equal to negative 45. I'm going to just do with the mathematical version here. It says how long till it hits the ground. So let's use our math version, and we're going to say, okay, what do we all know about this? So our initial velocity, v1, was equal to 40 meters per second. The final velocity, we're not quite sure. How long until it hits the ground? That's what we want to find out. So I'm going to put a question mark by that one. My acceleration. Now, remember, we said up was positive for this one, so downwards is going to be negative 10 meters per second squared. And our delta y is going to be equal to negative 45 meters because it started, like here's our original diagram, we're starting here and we're ending there. So here's our delta y, which is in the downwards or negative direction. So that's why it's a negative 45. We've got to be really careful about those directions. Again, we're going to use equation number 1. So we'll say that delta y is equal to v1 times delta t. plus 1/2 a delta t squared. So delta y is equal to negative 45 is equal to 40 times delta t plus half times negative 10. So I'll just say minus 5. Hope you're okay with that. Half of negative 10 is minus 5 delta t squared. So this is a quadratic formula, isn't it? It's a quadratic equation. It looks a little crazy, so you know what I'll do first is I'm going to say, I think your math brains are going to go, that looks nicer to me. If I say let x equal delta t, and so as soon as I do that, then it gets minus 45 equals 40x minus 5x squared. Now I'm going to rearrange things so it's going to be equal to 0, and I kind of like to have the quadratic term, that x squared term, is positive, so I'm going to say 5x squared minus 40x minus 45 is equal to 0. And then the next thing I notice is that I can divide everything by 5. Right? I can factor out a 5 on the left-hand side. In fact, if I divide 0 by 5. So if I divide both sides, I get x squared minus 8x minus 9 equals 0. Can we factor that? So what do I need? It's a simple one because x is equal to 1. So I need two numbers that will multiply out to negative 9. So some number times some number is equal to negative 9, and I need them to add up to minus 8. So I think if I have a plus 1 and a negative 9, plus 1 and a negative 9, that should work. So I'm going to say x plus 1 and then x minus 9 is equal to 0. So my two possibilities are x is equal to negative 1 and x is equal to 9. So again, thinking about it in terms of time, I'll just switch it back here. Time could be negative 1 seconds, or the time could be 9 seconds. Can I go back in time? Well, yeah, we can't really quite do time travel on this one, but the idea would be if this was still part of a constant acceleration, if you weren't just standing there before you threw the ball, but the ball was, from the ground being thrown up, if we went and followed this whole, here maybe I'll do it here, if we follow this pathwards downwards, right, and if at negative 1 time was when somebody launched it 1 second later, so we're at 0, it would be here. If that makes sense to you, great. If not, don't worry about it. So I'm going to say, no, we don't want negative time. Here's our answer at 9 seconds. Okay, so there's the math version. By the way, if this doesn't factor nicely, you could also use, if it's not friendly, you could use that quadratic equation. So have that quadratic equation in your notes so that you can use it, and if you want to write it out and even do an example of using the quadratic equation just to remind yourself, I'm okay with that, and you can bring those notes into your quizzes and tests. How fast is it moving when it hits the ground? So it's very similar here. We're going to use all those ones again, but the difference now is that we're going to say, well, what we want to figure out is v2. So we can't use equation number 1 because equation number 1 doesn't have a v2. I'd say there's more than one thing you could do. I'd say a nice one would be equation number 4 would say v2 is equal to v1 plus a delta t. And it kind of makes sense, is that the final velocity is going to be the initial velocity plus the acceleration. It increases by 10 every second. So we've gone, originally we were going 40 in a positive direction. And then we said plus, it changes by 10 downwards each second, and that was for 9 seconds. So we're going to get 40 minus 90, so we're going to get minus 50 meters per second. But really, we can even figure it out. Look at this from our graph. And I was, actually, I got it right here when I put this right on the 9, even though I didn't know for sure. So that means that at 8 seconds it was going downwards at 40. At 9 seconds it would be going downwards at 50. So that kind of works out. Alright, and so again with my diagram I should have drawn the line just right there, because it would have hit the ground exactly on that second spot. Okay, so hope this is going well for you. I know the math is getting a little complicated. So I'm going to do the same thing again. I'm going to finish the video. I'll let you try to do your turn. It's the same question as before, but we're going to throw it downwards instead of upwards. I wonder if for this one the motion is all downwards, right? So you're going down at 40. Maybe it's going down fast. The next time it's going even faster, something like that. Maybe for this one, it would be better to say that downwards is positive, since all the motion and everything is downwards. I'm also going to say let's make this height 45 meters. So again, it's kind of friendly. So could you do a motion map and a velocity time graph and then solve those two questions? And the answer will be in our next video.